Good morning, good afternoon, good evening, wherever you may be. Today I would like to present about the differences between a Geoserver and an API, and show you a demo of what the differences may be and how you can work with them in a simple as possible manner. So, let's get cracking, shall we? I'd love to essentially draw out what we've got here first before we get fully into the code. So, the general setup as it stands, let's go from bottom to top because we're built like that. Essentially, we will have a Postgres database, and in there we are going to put a bunch of geographical data. This uses something called postgis as a means of serializing it and being able to work with it in the Postgres setup. And then from here, we're going to load in a bunch of data. This data comes from the company that I am currently positioned at, Leander, and it is made public through a governmental organization called PDOK. But basically what we will have is a lot of electricity cables, so lots of lines that sort of look like this, and also meter data. This data is fake, it's not actual data, but essentially just places on a map where we will put metadata, quote unquote metadata, that's saying, oh, this meter had a problem, it was problem number 3, and this meter had problem number 2, or whatever. So yeah, that's the general setup for the database, and we will load this data in, we will load this data in using a mixture of Python, SQL Alchemy, and yeah, I mean, you get it, SQL Alchemy, and the Python adapter, which is called PG2 for Postgres. So it's a conversion of something called a GeoPackage, which we've taken from PDOK, and a set of CSV data that is available in the repository for the meters. So that is our data setup. We will then run this and something called PgAdmin, which is essentially a overview. It's just a client, a user interface to look at Postgres data. We will run PgAdmin and Geoserver, as well as the Postgres database itself, all through Docker. So can I get a different color quickly? Yes, I can. Excellent. So all of this we will run from Docker. It's a container service, which you pull images from and then can run locally on your computer without having too much setup. And once all of these 3 things are running, we will then load in our data in here, and then from here we will run a separate API, which we will write in Fast API. So let's call this our Geoapi, and this is using then Fast API, and which is then written in Python, and again our SQL Alchemy setup. So language-wise, we have that's Garbo, SQL Alchemy. Very bad at spelling that. So the Geoapi, which is then written Fast API, SQL Alchemy, and then the thing before. So the predominant 2 languages that we have running here are Python for the stuff that is written for loading in data, and the Fast API, and then Geoserver is actually written in Java. Although we will not be doing too much stuff with the back end of the Geoserver, as most of it will go through the web user interface that comes packaged with it. And then last but not least, we have our front end. And because I am predominantly a Python developer, this is written in Streamlit. And for the maps, we use something called folium, which is a wrapper around a JavaScript library, which is called Leaflet. And out of the box, Leaflet usually uses OpenStreetMap, although we will show a bunch of different base maps. So all of this is then set up, and using a Docker Compose file, we will run all these things, set up volumes to store the data for when the pod is killed. Also through this Docker Compose setup, and then we will also throw up a network, also from Docker Compose. Wow, my handwriting is getting worse as the time goes on. A network, which means that everything can talk to each other But the main thing that we care about is that the front end can talk to the Geoserver and the Geoapi, and that the Geoapi and the PostgAdmin and the Geoserver itself can talk to Postgres. So, after this set of drawings of a madman, I hope we have some sort of overview of what the actual goodness gracious is going on here. And from bottom to top, I will take you through the code and the user interfaces and loading in the data. And for the Geoapi and the front end, I will show off a bit of what the code that is written there and sort of discuss the pros and cons of using one or the other. And if we get rid of all of this now real quick, if this is something we can do. Excellent news. What the main thing that we're comparing here, after all of that huge amount of setup, is what the actual difference is between having a Geoserver on one side and a Geoapi on the other. So the way that the Geoserver works is that it takes data from Postgres and then builds what are called tiles, which are literally just X by Y sized images showing the data that you care about on them. So in this instance, that is then some cables that we have. And then what this Geoserver does is it pulls the data and renders them in a set of images, essentially. And then what the front end does is it pulls all of these images from this tile server and then renders them on an interactive map that you will then see in the Streamlit front end. Wow, that was doo-doo. So all of this is completely separate. There is no data loaded into the well, I mean, the images are there, but essentially you can consider it as a sort of iframe from the front end to the Geoserver, which thus means for large amounts of data, it should render in much more smoothly than if you were to load in all of the data to the browser, which is essentially what the Geoapi does. So rather than the Geoapi serving a bunch of images, what it's actually doing, it's serving a bunch of what are called GeoJSON. And there is a standard for this, and I'm really bad with my acronyms. I think it's OGI, Open Geographical Institute Standard or something. But basically what you end up with is a list of dictionaries, which then have features in, and then per feature, we then have the coordinates, so the X, Y, whatnots. And for each coordinate, we then have properties. Well, I've made a mess of this. Which then tell us about what are being placed in the coordinates. And so when we run the Geoapi, all we're doing is actually making REST requests and using this GeoJSON data to then render the lines on the map. So this will load all of the data into the browser, which for very large amounts of data will have larger issues, which we will see. Also, with regards to this whole setup, we're running on a Mac Mini from 6 years ago, more than that, 6 years ago, and it's all a lot of the main heavy lifting is in Docker. So we will likely see. I'll show you later, but in the CPU usage and whatnot, you will likely see this poor little machine cooking. But that is not the end of the world. All I mean to say with this is that the rendering times between both will suffer for this, because essentially the larger the machine and the more compute power there is for the Geoserver, the quicker this tile service will render. And essentially for the Geoapi, it's purely based on how quick the browser itself and like the front end code that you're running that pulls data and then renders it. That is then the thing that affects the speed and the interactive ability of it. So with regards to small amounts of data and quick rendering and interactivity, you'll see that the API approach is quite good. As soon as you go above sort of 10,000 or so points, let's say, you will see that this will start to suffer, at least in the Streamlit approach. There are much cleaner and faster libraries to do this in JavaScript, but this is for predominantly Python developers who want to get something running very quickly. And yeah, the Geoserver, yeah, it should render in okay, but you will notice it renders in the XY tiles somewhat crunchy as well, but that's purely because we're running, as I say, in this Docker thing. But yeah, let's get to it, shall we? So there are a couple things that I will assume to some extent. I expect that there is Docker and Docker Compose, Postgres, yeah, essentially a bunch of libraries installed up top. I'm running the Postgres stuff not on the default port because I have a lot of other things going on in the background of this computer. So it will not be 5432, which is the default Postgres stuff, it will be 5434, and you'll notice that throughout the code that we end up seeing. So essentially the three main commands that we care about are Docker Compose up, and then -d is detached. So if you want to see what's going on in all the things you're running, you can just remove the -d. And then once that's running, we will load in the data, which will then just be, I've not included it here, I'll add that later, which will just be a Python run load data.py script. And then from there, we will do some slight configuration in the Geoserver web UI. We will then run the GeoApi and run the front end, and then do some, little comparisons. So, first of all, let's get started, shall we? I have cloned the repository that you just saw locally. I have pulled the data from PDOK locally. This is then the URL for that. What you'll notice is that it'll ask you to download. If you're curious for more information on it, you can, where are we? Go away. You can look into PDOK themselves. You do PDOK Leander. That should give you what we're looking for. We're using this data set. And while we're here, we can have a quick look on how they've done it. This is also a tile server. I believe they're using something called Tagola, which is a Go-based tile server and not the Geoserver that we're used to. But if we zoom in, hopefully, I would love it if they would show the information that we care about. I mean, if not, this just proves, there we go, we've got it loaded in now. I wonder what was going on there. Essentially, all of the purple cables are what are called middle voltage. Usually I'm doing this in Dutch, so my English could be a bit rusty in these places. But the purple is then the middle voltage. So they're like the green boxes that you see in the streets, and then the cables under the floors, in the Netherlands at least. The brown ones are then the low voltage, and then the big blue ones that you see kind of going directly across the country. These are then the high voltage networks. These are the ones where you see the big towers and you see the cables above land. So that's basically what we're trying to plot, and then on top of it I'm going to add our own fake meter data, which will then just be sort of small flags or little blobs that tell us a bit more about what's going on with the meters. So that's the data set that we're using. The link that I've included goes directly to, not the RSS feed. It's always a bit of a pain to navigate these things. I think we said metadata and some other stuff. If we look at the metadata, then you go to the national blah blah blah, and then all I've done is downloaded, I think it was one of these. Essentially, you can get the geo package if you directly click this link. So that's what we need. That's that one. And then this one I will include. This one has been included as a zip file, so you'll need to make sure you unzip it before we try and load that in as well. And I'm working with virtual environments for the Python stuff. It's just sort of built into VS Code here, so then these are then all of the Python things that I'm running, that I'm using, all the Python packages that I'm using, and the environment is then based on the two requirements files, one for the front end and one for the API. The API one is the one that is mainly used in the load data, so let's have a quick look at that. Here we read in SQL Alchemy, GeoAlchemy, which is then an extension that allows you to work with geometry-based objects from Postgres, pandas to do some minor data manipulation, and GeoPandas also to deal with the geo package stuff. They have a lot of nice built-in things that will do that. GeoPandas, by the way, is then sort of based on this package called Fiona, so if you don't want to use GeoPandas, you could do it manually through there. But this is a quick and simple setup. For the connections, oh, I've started in the wrong place, huh? Should have gone somewhere else, excuse me. So to start with, what we're going to do is load up the Docker Compose. These are the ports that we will then look for it. It's using this postgis image that comes with the options for extensions already downloaded for Postgres. We've got Postgres for the username password. For PgAdmin, it's a general sort of setup where it's just like, run it on this port for us. There's a general volume stuff in case we change anything, although we're not going to do that too much. We've got defaults for the password, which is then admin for when you log in initially. And we will then we will also run the Geoserver using their the OSGeo default image. I'm using 2.25.2, but in the future you can just update this and we'll have newer versions. And then everything that requires information from each different place, we are then calling through this network and then using a bridge driver to do so. So we have named a database here, and we've said, okay, this is then the network that we're going to use, and then for each of the other things that require it, we then call the thing out in the networks tab. I've included Geoserver there, but I guess it's not inherently necessary. Get rid of that in the future. And then yeah, for the volumes, let's add Geoserver over here as well. In case we make changes and wish to have these stuff persevere. So let's do it like that, shall we? So we call Geoserver, and in the data directory is where we will save any changes that we make. So this will take a while, especially on my poor old machine. So I will likely do a jump cut. Excuse me. From when I run this to when it is finished running, and then I will show you the interfaces that we have up and running. So let's go, and in a couple minutes. Alrighty, we've got everything up and running now. Took a while to pull, as you can see. So if we take a look at what we've got running here, we've got a container group, which the name comes from directly the folder that you run the Docker Compose in. We have the Postgres thing that we set up, we have the admin container, and we have Geoserver. These names, by the way, are based on the container name that you put here. Yeah, if we have a quick look, we see that the database was created, the Postgres extension was added to various different users and different places. Yeah, we have something running that we can then connect to as we like. And then that is the port that we are listening to locally, so like in the container itself. And because we forwarded that port to 5434, we should then be able to access the database based on that endpoint. This is the PgAdmin setup. This is very simple, just run the thing using gunicorn on the main local port, which the default for everyone, by the way, is 80. So we're just running the thing on the default and then porting that to 5050. So if we go to localhost 5050, we should see our user interface. And this is the Geoserver setup. It essentially pulls the extensions and runs and builds the Java package, Java software that is used in the Docker image, and it will use various different sort of default loggings and caches of where stuff is. The Docker thing that they wrote, for some reason, they have decided to use the depot extensions for everything. Not entirely sure why, but if you ever see any errors, that is their default error. And then there's some general information about the things that we're running. The whole thing is using Tomcat, which is a Apache thing written in Java that essentially runs web servers for you. So in the background, that's everything that's sort of going on there. And then we run in a bunch of different command line arguments. We load in all of the example data that comes with it out of the box in the Docker image that we pull from in this instance. It does a bunch of setup stuff, looking for grid sets, looking for layers, sorting out the catalog that you'll see in the front in a moment. After all of this, then serving it on port 8080, which is the default for Geoserver. And in this instance, we're just porting that Geoserver 8080 endpoint to our localhost 8080 endpoint. So if we go there, we should also see it. So next step, let us quickly just show off the UIs. They come with something sort of loaded in immediately. So here, this is the admin password that we included in our Docker Compose. To connect a server, you need to register it. In this instance, I'm going to call this Netherlands Production. We have a host name. All of this information you can find back in the README. Everything that I'm doing is running on a Mac, as I said earlier. So this will likely change depending on the machine that you're running on. But essentially, Docker, at least the more modern versions of it, reveal a sort of internal host that you can connect to. I think the Windows version is then just docker.host.internal. But if you're not running Mac, then double check that this is the sort of default internal port that Docker reveals for your machine. So we've got the host, we've got the port that we set up, which is 5434 in this instance. The default database is Postgres, so we can leave that. The username that we set up in our Docker Compose is also Postgres. where are we? Yeah, default username and password Postgres. So we can put that in there, and then yeah, as we just saw, our password is also Postgres. So we're Postgresing everywhere. So in theory, we should then be able to save, and then this will allow us to view everything that we have currently in our stuff. This is stuff that I did previously, so we can ignore that for the moment. Everything that we will be doing is in public, and this is then the postgis spatial reference stuff that gets loaded in when you do that extension. So yeah, next step is to sort of load the data in, I guess. Let's have a quick relook at our load data stuff. So we've connected, because of my bad memory, I've done this in a bit of a weird order, but essentially SQL Alchemy works based on engines. We are using the localhost port of this because we are talking to Docker externally from Docker. We will add the extension to the tables that we care about, running this simple text command. SQL Alchemy uses bases. SQL Alchemy uses it's an object relation management system, ORM. And essentially these are just the names of the tables that we will create and where we will put them. So what we can do is specify all of the columns and stuff that we want to use. For the meters, we have extra information. So when did we get the data? Which address is it? So in this instance, postcode and house number. The information we were talking about, which is then problem 1, problem 2, problem 3. And then the geographical information for the meters, they're all points, and for everything else, they are strings, line strings, excuse me. Yeah, that's the general setup. And then with SQL Alchemy, you can use a create all statement based on the engine that you put in, and then this will make all of the tables. And then from there, we're going to read in the CSV data that we have unzipped. Be sure to unzip that beforehand. We're going to print what it looks like in our terminal, just so we can see what's going on. And then we're going to insert everything. And then with regards to the cable data, we are pulling from gpackage that is there, and we know, having looked into what layers there are using Fiona previously, that all of the layer names that we care about are called these things. This is the Dutch for low voltage cables, middle voltage cables, and high voltage cables. And what we're doing is we're just pulling in the layer data as a data frame, setting the shape as a geometry object with the Dutch projections, because all of this data is Dutch data. They made their own way of projecting the points and lines onto a map. So the world uses a different number that I'm blanking on at the moment, but the Dutch one is then this. So we need to specify this, otherwise we end up with like slightly shifted points later on, which will be a pain in the bottom. And then from there, we will do the insert for each of the lines as well. So we're just iterating over name and the SQL Alchemy model that we are going to use to insert it. So we're just saying insert in the model that we care about, the new data that we got. So let us do that. I think I'm going to need to do another, let's do this in a new terminal actually. I think I'm going to need to do another jump cut because this will also take a while to do. But essentially what we can do here, because we've activated our virtual environment with all the requirements in, we can then just say Python load data, and it will then run through our print points. So we've created our extension, which we saw earlier. We're printing the data frame that we've run in. So here we have like all the timestamps we're talking about, the addresses, the different types. And then, yeah, this is essentially a binary hex code sort of thing, which is the way the postgis deals with shape data, geometry data, excuse me. So anytime you see this, you will see this sort of stuff with Postgres. And if we go back to our PgAdmin stuff and refresh, we now see all the tables that we created. And as the data loads in, we will also be able to take a look at the data. This will take a while, so we will do our jump cut now, and we can come back to it when it's all loaded in. Alrighty, yes, let's look. Seems like everything inserted fairly okay. No errors coming from the load script. So in theory, we should have all of our data in Postgres now. So let's run the first 100 rows. So that's the meters one. That will be the LS cables one. Oh, by the way, PgAdmin has geometry viewer built in, so you can already have some sort of idea of what we may end up getting if we choose the first 100 meters, for example. Cool. Yeah, so then this will be the cables. You'll notice that because these are lines, you will have some that are very long and some that are very short, depending on how long the line is. And then this is then what this will look like. This is then our long line by the looks of things. If you click it, then you'll get the idea of it. As it's built up with lots of smaller lines. Excuse me. There you go, 25. Cool. And then exactly the same idea for all of the others, just at different levels. This is then the MS one. It's just higher up. And then the HS one. This is exactly the same idea again, but then on a grander scale. This is then across country, more than across street. But in any case, we now have all the data in our tables that we care about. So let us take a cheeky look at the, get away from that. Oh yeah, also with regards to the data, we can then see our volumes are now also pretty full. We now have in our database 100 megabytes of data. So that is nice and good. But if we go back to our containers, we can then have a quick look at the Geoserver. What you'll notice if you click on it though, you will get the teapot, because Geoserver actually runs not at the root, but it runs at geoserver/web. So this is then what we've got. The default, I don't remember if we specified it in the Docker Compose, but if not, you can find it on the Geoserver website. But the default username password is admin and then Geoserver. So now we can log in. Come on, chug. And then we can have just while we're here, a quick little look on some of the example data that they come with. Remember, when we looked at the logs, it was talking about various different map layers basically. And so what you can do is say, well, I'd love to I don't know, look at these countries. You can click on the open layers, and if everything renders correctly, you should then see an example of what that layer looks like. And in theory, we can then click on it too. So this is Algeria we've clicked on apparently. And if we zoom, we should be able to do other stuff too. And then this is of course the Netherlands, so then some stuff there. So yeah, the Geoserver comes with a lot of example data. So that is nice for us. There was one that's kind of nice to look at for what we're doing. Where was it again? Subcities, Spearfish. I mean, this will do on it. Essentially, this is then the roads in the country of Tasmania, and so then we will also see stuff like this, but then on a grander scale in the Netherlands for all of our cables. Yeah, so the next thing to start with is to create a new workspace. Workspaces are essentially just folder headings that you can then add your stuff under them. In this instance, because we're using a front end that calls the tile services, the names will need to match up with what we have in our front end. The namespace URI doesn't really matter. This is just for you to find back, but the name itself is used other places. So make sure it matches if you change it. Yes, so now we've made our default NL, short for the Netherlands. Let us add a new data store. These are the default ones that we were looking at before. The Tasmania one is then from top, as far as I understand, TOPP. But in our instance, we're going to add a new data store. We're going to add a postgres database because that's what we've set up. We're going to call it NL as well. And then, yeah, this is Dutch cable data. Doesn't super matter, it's just for us to know. And then we will use the same login information, I believe, as PgAdmin because, I say I believe, I'm pretty sure. It's been a while since I've looked at this. Let's find out in any case. So it should be that. We've got our port information, and then we know that all of our stuff is called Postgres because we were very slap happy with the naming of everything. Don't know why, but Geoserver provides a default password. That will not work. We have Postgres in this. Everything else we can sort of leave as defaults. You can change it if you like, but it's just essentially how does Geoserver interact with the Postgres tables. So there we go, and then these are all the table names that we included. Maybe there is a better way of doing this, but as it stands, I only know of this method. Essentially what we're going to do is publish each layer. You can change a lot of different things as you go through these tabs, but the main one that we need to make sure we have sorted is that the boundary boxes of the layer are included. And if you click here, it will then initially compute the minimum and maximum of the Y and X of each of the data points. So the box that you would originally load in on will make sure it covers everything. And then these are then the latitude, longitude boxes, the sort of world coordinate system that we're used to seeing. So yeah, that will then mean that when the thing is initially zoomed in on, we will make sure that everything is included. So we can save that, and then we can do that 4 more times. We have essentially the name of the store, and then the name of the table, and then that is what is considered the layer name. So we're just going to go back through them, and now, publish, compute from naked bounds, save, next, doop-a-doop-a-doop, doop-a-doop-a-doop, skip-it-up-a-doop, nyam. And then last one, so we've got the meters, ls, and highest. What have we got? Yeah, so ms is the last one. Wonderful news. Oopsie daisy. Wonderful news. So then these are all there now, and if we go back to our layer preview, we should also be able to see them. Let us do the high voltage ones, because there's less of that, so it should have less problems rendering it. But yeah, here we are. So essentially, this is the layer that now people can call from their various front ends, and you'll notice that it does render in the tiles as we mentioned before. You'll notice that they cut off as squares as you pull them around. But yeah, so basically the Geoserver is sort of set up for where we are now, and all the front ends will do is essentially target this server and pull in the images as we mentioned before. So that's that all nice and groovy. Let us now. Oh, in fact, while we're here, excuse me, last but not least, if you want to change the way they look, so per default, when we created our high voltage stuff, it gave the styling of blue, and that is just sort of the default that Geoserver gives all line strings. However, if we want to make a new one, we can say, give us a new style. This is going to be our super cool new purple line. We're going to add it to the workspace that we are working in. We are going to make a line object, and we're going to base it on the default line. And so what we can do is copy the styling of that. This, by the way, is XML. So if you look into how they do the XML of the different descriptors, is using the OpenGIS this thing. So as long as you make sure you abide by this schema logic, you can sort of do what you like with regards to how things look. We're being very, very simple though. We're just going to say we're going to make purple line, and it's then a solid purple line. Yeah, and then we're just going to grab the CSS for that, which we're just going to say hex code for. Should we just do lilac just to really mess with our brains? So this number corresponds to a sort of lilac color, so that's exciting. So we're going to shove that in. And then save that. So we now have a thing called purple line, and it is with that hex code, and it can be found in that workspace, excuse me. And then if we go back to our layers that we had, and we say, let's open this, and we want to change the way that the high voltage cables are shown. We can see here the default was the line that we saw a minute ago, and we should be able to find back in NL our purple line. And so now it will be a sort of lilac color instead of the default blue. And yeah, as you get used to working with the style sheets and stuff, you can then do more and more crazy things. But for us, this is then what our high voltage cables will look like in our front ends now. So, wonderful news. We've changed some styles, and we made it lilac. So, next port of call is to run the Geoapi. Let us do that. So here we're just going to run our Python Geoapi main. It's essentially this folder, this script. All that is in this folder is some quote-unquote schemas from Pydantic. Essentially, how does the data look like when you call the API? We have a database connection, which is basically the same thing as what we saw for the load data. It's all the models that we saw, and then the connection object, of course. And then this is where the main magic happens, essentially. We have a fast API with these general description parameters, so Geoapi that uses REST. We add some middleware for us to talk to it from any endpoint. If you want to be more specific, then by all means. The star is just a wildcard for let us connect to this from anywhere. We have a root endpoint, so people can test our API. So if we go to just localhost and then the thing that it's serving at, you should then see this in your browser. We have 4 different endpoints. one for the meters, which gives just the last X amount that you put in. So you can set this to 100 and you'll get 100 back in a list of dictionaries. And with regards to the GeoJSON format, the OGI thing that I mentioned earlier, I really hope it's OGI, I'm going to look very silly. In any case, the standard format of GeoJSON data, we're pulling from a package called GeoJSON Pydantic. And with this, we can just say, we want to make a collection, so essentially a dictionary. It's going to be called feature collection, which is then the standard. And then in the features, we want a list of feature objects, which again, another dictionary with a type feature. And then for the meters, these are all points, which then also comes with its own format with a type point. And then a, 2 is essentially a list of coordinates. So X and Y. And then the corresponding properties for that. So we have ID, timestamp, address, and info that we saw from our models. And then it's just iterating through all of the meters that you called from Postgres using the select from the model with the limit. Coolly-ooly. And then essentially the same idea for everything else. However, it's slightly different for the coordinates because this is then a list of lists. So we have our cable in our list of cables. This happens to be the low voltage. And essentially we're saying, give me the shape object as XY coordinates as a zip of that. So it's just a list. And then give me the X and Y separated and put it in a list. So list comprehension list with lots of smaller lists in it. And in this instance, for all the cables, we only have the ID properties. So then the properties is very, very small. Yeah, and then we have the same information for everything. Just then LS, MS, IS, high voltage, low voltage, medium voltage. Yeah, so let's run that. Very simple. The API last thing. To make things standard, all I've done is essentially provided a wrapper around it. So here we say, pull the app from the API thing we just saw and run it on this port. So rather than running uvicorn itself from the browser, it's always something that I forget the exact formatting of. We can then just be very simple and say, python main.py. Oh, I'm not Geoapi either. That's why you go from your notes. So if we run this, we should see that localhost spins up the fast API at this endpoint. So let's do that. Here we go. 127 blah 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 is another way of saying localhost. So what we can do now is say open localhost at 8090, and here we see our root, which is then the dictionary welcome to the GeoAPI. And then the wonderful thing about Fast API is that it builds Swagger documentation for you out of the box. So then you can interact with it from this point as well. So see the endpoint that we just saw, we can say, give me the root endpoint with this, essentially this curl command, which will then give us the response that we saw earlier. And just to double check that everything is working as expected, we can then also pull our meters. So try it out, give me the last 5. And if we execute, we should then see a feature collection, which we saw, a list of features. Here's our list, and then for each one we will have the feature type, the geometry of the feature, which is then a point type in this instance for the meters, and the corresponding coordinates. These coordinates are the Dutch coordinate system that I was mentioning before. There are ways of projecting that we will show in the front end to go from this number to like the regular XY latitude longitude that we're used to seeing in the rest of the world. And in this instance, this meter then happens to have these properties. So it happens to be this address and this type. Cool. And then, yeah, there's the rest of our feature collection. Also, if you're curious, we can just go to the URL directly. This is the equivalent of running the curl get command. So we can do that as well. And then that's just our thing that we were seeing in our docs as well. If you didn't have the Swagger documentation, this would then be your way of looking at it, or just running the curl command directly. But because Fast API makes this for us out of the box, it's nice to use it. So that exists. So we now have GeoAPI, we have Geoserver running. Let us open another window and have a quick look at the front-end code that we've got here. All of this is running based on Streamlit and Folium. And then the projection from Dutch coordinates to world coordinates, which is necessary for Folium, is then using PyProj. Essentially takes coordinates from one system and puts them in another system using a transformer. We have a set of utility functions used to do the transformation. So this is the Dutch one, this is the world one. It's called Rijkswater or something. Doesn't super matter. This is Dutch, this is world. And here we're saying get some data. In this instance, the default is the high voltage cables, using requests and return a response model object that we can then get the status information from, the JSON from, etc., etc. This is where the magic happens. This uses a Streamlit decorator to cache the data for X amount of seconds. TTL is time to something, essentially time of death, basically time to load, maybe. Basically, when the call to get the data again is done. So you only need to run it, load it in once, and then it will stay the same for this period. And then if you run it in again, then it will stay the same for that period again. We do that to make less calls to the APIs. This is then the thing. So we've got the response object. We then get the JSON, and we do some minor data manipulation to get it in a format that the front end can show it. Essentially, we're saying, give me the JSON, unpack it, give me the latitude and longitude as lat long from these coordinates that we had, that we saw from our JSON, and then transform them from world to new using the transformer that we created further up. Exactly the same idea for load meters, however, we need to deal with list versus points again, so then that's why there is a distinction. And that's that for loading the data in. And then this one script runs what you will see in a second, a dashboard with this general page configuration. You'll see a big title with dashboard at the top. You'll see two tabs, one with Geoserver above it and one with PgApi above it. And we will use the data that we load in to make two different maps, one showing off the tile server stuff from Geoserver, essentially saying read in a folium map, give me a, so the default here is then the open street map, as you see there, the tiles. And then we're going to give a couple other options, so there's Cartodb positron, which is a light version of something from somewhere. I need to double check where it's coming from exactly. I'm not sure. You can find out more at the leaflet extras. I need to double check that, that's not great. And so we will load in the thing, we will specify the default as the light version, and then there will be some options on the top right of the map to then change this base thing. And then we have the layer list, so this was then the store and then the name of the layer. So that's what we've got here. Here we can choose between showing all of them by default or only showing one. It's very just sort of simple default. If the layer is in the one that we want to show, then show it, and if not, then don't. And then yeah, this is the way that the tile server is called. Folium has a WMS tile layer endpoint, and we know that the URL is then the local host that we had. It's 8080, and then the Geoserver default to serve all of the tile servers is then /WMS, and then you can specify the name and then the format that you want it out. So we're just giving it as PNGs. The layer that we're running, excuse me, so the name will show up on the front end, so you can then click it. You could choose a different name if you like, but this is where we need to make sure that we've got this perfect. And then some general sort of default values of how it looks. Yeah, and then also this is a caching function to only change if the data changes. That's all this session state stuff that we have here. So that's the Geoserver one, and then we have something very similar for the PGApi one. Essentially pull the same default maps, give us for each of the cable types a different color with a different polyline. So here we're using polyline and the specific latitude and longitude points. With the color that we've arbitrarily specified here, you can do what you like with that, and then we're going to add it to this cable group so you can turn it on and off in the same way that you could do the map layers from before. And essentially the same idea, but then using markers for the meters, because the meters are just points, and also we're specifying the extra property information as a pop-up, so when you click on it you will then see these, and using a green icon. So that's basically that. And for the map size, we're using a utility package that someone has created, which will essentially look for the maximum window width and then give us 200 pixels less from that, and then similar idea for the screen height. So in theory, the map size should always be fairly central and big based on whatever window size you're looking at. So that's that function. We call it in to get the window heights, and then we use a renderer of the maps that we're creating. So create the map and then make it static with the max width and max height that we had. And then, yeah, these are the two tabs that we were looking at. So give a header of PyGeoApi and Geoserver in the front end, give us a slider for the PyGeoApi to read in the limits. So the initial will be 100, so we should see 100 points from the meters, the LS, MS, and RS, and then we will try increasing this and seeing at what moment the map has troubles rendering, because that is essentially the comparison here. Yes, and then if we go back to our README, we see that we need to use Streamlit run to show the dashboard. So let's do that. This will then open localhost at the default point that it renders these front ends, which is 8501 for the Streamlit stuff. So here we are. This is our map. These are our layers. We've started with the light version, as we saw. We can change it to OpenStreetMap. We can make it dark to maybe show up the lilac high voltage things that we've got. Because of our if-else statement, we're only showing high at the moment, but we can add the meters, for example, and you'll start seeing them slowly render in. Now is a moment to show how much this will affect your PC, because it is very, very computer intensive. So if you do this in production, make sure you run this on a different server than other front ends. These are all of the CPUs that are running on my machine. As you see, they're fully cooking to make sure this renders. The memory is about half and the swap is almost full. And so you'll see it very slowly start to render in, purely based on how many meters there are. And this is about 30,000 or so that it's trying to render in this map in a very, very small Docker container. But it will get there in the end. But yeah, so as you notice that it pulls in the things as the tile squares that we saw before. Let us give it a rest, and let us try and pull in the MS ones. So we'll notice from top down it will start rendering in the things. But yeah, that's basically sort of as we're cooking, that's what it's ending up as. Yeah, the only limit of how fast this runs in is, I mean, the speed of Java and Tomcat, which for most things is yeah, very like performant enough, and just the amount of CPUs that you're running the Geoserver with, which in this instance is quite small. Yeah, so you'll notice the render gets more and more, oopsie daisy, more and more detailed as you go in, and then we can jump between various different ones. So this is then the light version, this is then the OpenStreetMap, and yeah, these are then all of the the middle voltage, medium voltage cables, and high voltage. We can try and render everything in. Depending on the zoom, you will then see more or less. The red are the meters. In this instance, we've not made a distinction between the way the low and high look. So that is all the low, and that is all the medium. So bear that in mind. We could go back to our styles and change that if we like, but I think we get the point, right? Yeah, as it stands, these are then the meters that we happen to have zoomed in on. As you zoom out, you will notice that it will attempt to render everything in, but it will struggle very quickly. So give it a bit of a break, then it will attempt to render things in as we go. But yeah, as I say, the thing that is running this is a very, very small Docker image, Docker container, excuse me, so it will struggle. But yeah, that's the Geoserver stuff. Fairly performant considering how small everything is and the amount of data that we're trying to run through this thing. And if we go to the PyGeoAPI, this is the equivalent. As it stands, all of this is being rendered into the browser itself, so all the data is stored in the browser. At the moment, we're with a read-in of 100, and that is then fairly performant with regards to looking at stuff, and we can click on it and see this the meter, the address, the info, etc. And then because we're only reading in 100 somewhat randomly, the cables are then a bit confusing. We have all the tooltips and stuff. But if we attempt to increase the amount of rows, we can then see it will pull in new data and attempt to render it in real time whilst caching the GeoJSON stuff that we're pulling in. So you will notice very quickly that this is not as performant as the thing is before for the initial render in, but when the data is there, it is fairly performant with regards to this. It's purely based on how quick and capable is the browser and the local machine that it's running on. Is then your distinction. But yeah, if you go above, so in this instance we've got a limit amount, right, and we then have four endpoints. So at the moment we're running essentially 4,000 different geographical points in this. The moment you go past, yeah, as I say, about 10,000, so if that's then 3 or so, 2,500, you will notice that it will start struggling. So we're loading in, we did the meters, and then each cable load is then a different cable. So the data is then in the browser, and then this is Folium attempting to put it on the map, which is then the thing we're waiting for now. And yeah, this is as fast as the browser is essentially, and to some extent how fast Streamlit is. There are other front-end packages in Python that you can use. The one that I saw recently was, I think it's called TauPy, if my memory serves. But that is then also something you can look into if you really want to run Python-specific dashboards. However, I would look into using maybe Angular or some other JavaScript framework. So yeah, that's basically the summary. So to quickly, oh yeah, excuse me. So then we're fully cooking. That was then the thing. We're running our Streamlit thing, and so to close everything, we can just stop running each of the things. So that is the Streamlit dashboard shut, the PyGeoApi shut, and then if we go down to this, we can then also say stop all of the Docker Compose things by saying Docker Compose down. And so now everything should slowly stop itself after a couple minutes. Chug, 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 pulling the machine. Yeah, and then while we're waiting for that, quick overview summary. I'll close all these things now. We set up a Docker Compose with PgAdmin, postgis, and loaded some data in. We then connected a Geoserver to it using Docker Compose as well, and then manually putting in the connection settings. We then ran a GeoApi that was then calling the Postgres stuff and rendering it as GeoJSON using the globally recognized standards. And then we connected a front end which used in one tab the Geoserver data and in another tab the GeoApi data. One thing I want to mention lastly is that I happen to have written this API myself because I spent a lot of time doing that in the company that I'm at, and so I found it easier to connect everything. If writing APIs is not your forte, or if you want something a tad more out of the box, there is a project called PyGeoApi. Oh, it's OGC, not OGI. Well, in any case, that's the one. So they're the standards that you're matching. But yeah, you can then also use this instead of writing your own. That's very much up to you. They have quite a nice overview and stuff. Do they have the demo? Yeah, you can then play with their demo if you are curious. The problems that I was running into using this was essentially the conversion of units, because PyGeoApi is written for an international audience. Wow, this is really struggling at rendering. So not the Dutch unit system, and so the conversion was very tricky. So for me, and I also, with my background as well, very used to writing APIs, so for me it was just easier. But if that's not you, and you want to use a quick way of setting up a GeoApi, then that is another option. Or you can just copy what I've done here. Also good. Yeah, so I think that's about everything. Let me know how you get on. I'm curious to see any of your projects that end up using this sort of stuff. So be sure to reach out if you have something fun. And yeah, thank you for your time.